All right, in this section we are going to solve differential equations with power series. So in order to approach this topic, we need to talk about when we can solve a differential equation using a power series. And for that we're going to need a few definitions. So let's get right into some of those. And the first definition is the definition of a function being analytic. So we say that a function is analytic at a point if there exists a power series for that function centered at that point with a positive radius of convergence. So most of the functions that we deal with on a regular basis are analytic almost everywhere on their domains. Okay, well let's bring this into the context of differential equations. So let's consider the second order homogeneous linear differential equation. Okay, and let's write it in standard form. That would be dividing by this coefficient here of y double prime. All right, so we're going to say that a point is an ordinary point of the differential equation if both p of x and q of x are analytic at that particular point. And on the other hand, a point that is not an ordinary point, meaning at least one of p or q of x is not analytic at that point, such a point is called a singular point of the differential equation. Okay, let's look at a few differential equations and identify any singular points, if any. You can see that its p of x is 0 and its q of x is equal to 1. And these are analytic everywhere. So this differential equation has no singular points. Or you could say every point is ordinary. All right, what do we have here? Our p of x is negative e to the x, and our q of x is sine of x. So those are also analytic everywhere. And therefore, no singular points. Okay, so far this is very interesting. What about this one? Well, this one's not quite written in standard form. So let's divide by x, and we're going to have y double prime plus 1 over x y equals 0. And you can see here that we have a q of x, which is 1 over x. Now, q of x is not analytic at 0. In fact, 0 is not even in its domain. So we have x equals 0 being a singular point of this differential equation. The reason why we're bringing this up right now, and just so we can look ahead a little bit, is that because this particular differential equation has a singular point at 0, it turns out that the solution to this differential equation will not have a power series centered at 0. In other words, there won't be a Maclaurin series for the solution to this particular differential equation, which means we will not be able to use the particular technique we intend to use in order to solve this differential equation, which means we will not be able to solve this particular differential equation using a power series centered at 0. We could, however, solve it using a power series centered somewhere besides 0. All right, and in this case, we have a p of x, which is only analytic for positive values of x. So we could say that x equals 0 is a singular point. In fact, by the definition, all x values less than or equal to 0 would be considered singular points. Okay, let's summarize this in a big theorem about why we care about the distinction between ordinary and singular points. So this says, if you have an ordinary point of a second-order homogeneous linear differential equation, then you can solve the differential equation in terms of power series that are centered at whatever ordinary point you want. We usually choose 0 when we can. So in other words, the solution takes on this form. The radius of convergence of this power series will always be the distance from x0, where we're centering, to the nearest singular point, if such a singular point exists. Okay, so what remains is exactly how do we use a power series to solve a differential equation? Well, we'd like to solve higher order differential equations, of course, but in order to motivate the process, we're going to look at our first example, which is just a first order differential equation, one that we know how to solve a number of different ways, but we're going to see exactly what the process is solving it using a power series so that we can learn this process, and then we'll solve higher order differential equations in the next examples. All right, so we're going to work out the process on this little differential equation. And this is a good one to use because we actually know at least 3 different ways of solving it. Right? I mean, it's separable. You can write it that way and then just integrate both sides. It's a linear, so we could work out an integrating factor. Just look something like that. We're on our way. And it's also a first order homogeneous with constant coefficients. So it has the characteristic equation m plus 1 equals 0, and this is probably the easiest way to solve it, right? There we are. So we know this is the solution. Let's work this out using power series and see if we get the same thing. We ought to, because math always wins, right? So how are we going to work this out? Well, we're going to start by assuming we have the solution. And it's of the form of this power series, Cn x to the n. So note that we're centering this around 0, and 0 is indeed an ordinary point, so we're good to go. In fact, there are no singular points for this particular differential equation, which means that when we eventually do get a solution in terms of power series, the radius of convergence will be infinity. Okay, so we're going to need y prime, and we're going to need as many derivatives as we have in the differential equation. So here we only need y prime. Okay, so what is y prime? Well, y prime is n equals 1 to infinity of, now the n here comes down, we get n times Cn x to the n minus 1. So we just took the derivative of x to the n. Now, why did we start the index at n equal 1 and not n equals 0? Well, we could have started it at n equals 0, but if you did that, then you'll notice the first term of this would be n equals 0 anyway, because 0 times all that other stuff. So you might as well just start the series at n equals 1. And if we were to take more derivatives, y double prime, y triple prime, and so on, then the index would start at n equal 2, n equal 3, etc. So typically the starting index coincides with the order of the derivative. Okay, so now we're going to substitute into the differential equation. So the differential equation is y prime plus y equals 0. So y prime is this thing. And y is this guy. Okay, so our job is to figure out what conditions this imposes on Cn. We just need to figure out what the Cn's are, and then we're good. So, of course, in order to do that, we need to combine this to a single series, which means the first thing we ought to do is shift the index of summation so that they both match. So we want these to both be x to the k. Here we can see that we're going to let k be n minus 1, which also means that n is k plus 1. On this one, we're going to just see that k will be simply n. So that one's pretty straightforward. So what do we have here? Well, n is k plus 1. And when n is equal to 1, k is equal to 0. On this series, we're just switching the n's to the k's. All right, now we just need to combine to a single series. And note that the starting index matches for both of them, so we don't have to run any terms off. That's unusual. Usually you have to run 1 or 2 terms off of some of them. So we can just say right away that this is... And there we are. Okay. So the idea is, in order for this equality to hold, we must choose C0, C1, C2, C3, etc., so that this particular factor here works out to 0. Now remember that the general solution to a differential equation has a number of parameters matching the order of the differential equation. So this is a first order differential equation, which means we're expecting one parameter. How is that represented in our work so far? Well, what that means is one of the coefficients of the power series is free, and the rest are all set based on that first one. So we're just going to declare that C0 is the parameter, and everything will be based on C0. All right, so what does all this mean? Well, this has to equal 0. So now what we're going to do is solve for highest index of k. So the highest index here is ck plus 1, so we're going to isolate ck plus 1. We can see that that's negative ck over k plus 1. All right, this is called a recurrence relation. We're going to use it to generate all the constants. So remember earlier we said that one of them was free. Well, C0 is going to be the free constant. So we're just going to declare that C0 is C0. Yes, that's very groundbreaking. But the rest are all going to depend on C0. So we're now going to generate the constant C1. Now looking at the recurrence relation, we can see that C1 corresponds to a k value of 0. So what do we have here? Well, if our k value is 0, then this is negative C0 divided by 0 plus 1. So C1 is negative C0. Okay, now we're going to find C2. That corresponds to a k value of 1. So C2 is negative C1 divided by 1 plus 1, which is 2. All right, but we know what C1 is. C1 is negative C0, so this is in fact just C0 over 2. All right, now let's find C3. Now this corresponds to a k value of 2. So C3 is negative ck, k is 2, so this is negative C2, divided by k plus 1. So that would be 2 plus 1, which is 3. Okay, but C2 is C0 over 2. So this is going to be negative C0 over 2 times 3. Now you can see that what we're getting is a sequence of coefficients, C0, C1, C2, C3, etc., and they're all written in terms of C0. All right, well, what's C4 going to be? That's the k equal 3 case. So that's going to be negative C3 divided by 4. Well, C3 is negative C0 divided by 2 times 3. So this is actually going to be now positive C0 divided by 2 times 3 times 4. Let's do one more. C5 is negative C4 divided by 5. So this is the k equal 4 case. And you can see that since C4 is this thing, we're going to get negative C0 over 2 times 3 times 4 times 5. Now, very often, we will not see an obvious pattern here. In fact, most of the time you will not. But here, because this was such a straightforward problem that we applied this technique to, we actually can see a pattern quite nicely. It looks like we're generating factorials down there. In fact, why don't we write down the pattern for Cn? So notice that when the index of C is odd, we have a negative sign, and when the index of C is even, we have a positive sign. So that means that this is an alternating term, and the offset is simply negative 1 to the n. Of course, the numerator is C0 all the time, and it's divided by, well, at index 5, we have 5 factorial. At index 4, we have 4 factorial. At index 3, we have 3 factorial. So this is just going to be index n factorial. Okay. But recall that we defined y to be this. So Cn is negative 1 to the n, C0, and then 1 over n factorial, and x to the n. So we could write this as C0 times the sum. Remember, C0 is just a constant, and negative 1 to the n, x to the n over n factorial. And that would be our final answer. That is the series representing the family of solutions to that differential equation. And you may recognize this form here as e to the negative x. All right, so admittedly, this is certainly an inefficient way of working out the problem if we already have some other better way of doing it. So let's put our attention on second order differential equations where we have the non-constant coefficients and no other way of solving them, so we have to use series to work these out. All right, so here's one that we have no other way of solving, and it's second order, it's homogeneous, but it doesn't have constant coefficients because of this negative x in front of the y here. And it's certainly not a Cauchy-Euler equation or anything special like that. So yeah, we just have to use kind of the big wrench, which is power series. So what we're going to do is we're going to let y be of this form. And we're going to need y double prime. So to get there, we'll take y prime first. So that'll be n equal 1 to infinity of n Cn x to the n minus 1. And then let's take y double prime, which is the derivative of y prime, of course. So that'll be n equal 2 to infinity of n minus 1 Cn x to the n minus 2. So now we have all the ingredients we need. Let's go and put those into the differential equation. So there's the differential equation, and y double prime is this lovely thing, and y is this thing. Okay, so we're going to play the same game we've been playing. We ultimately want to have this as just a single summation of stuff equals 0. So we have sort of two gates to get through. The first is writing these both to the same power of x, right? So this is shifting the index of summation, so they're x to the k. Of course, the second gate to get through is running off terms as needed so that they all start at the same index. All right, so we're not quite ready to do any of that because of this x factor on the outside. So let's push that x inside its series. Okay, so to shift the index of summation, we're going to let k equal n minus 2 on this one, which of course means that n is k plus 2. And over here, we're going to let k equal n plus 1. So n is k minus 1. So we can see this is going to give us a k equals 0 to infinity. And all these n's will get replaced by k plus 2. And on this one, we can see that when n is equal to 0, k is equal to 1. And all the n's will get replaced by k minus 1. Okay, so we have the power of x's agreeing with each other, but we do not have the first index of the series agreeing with each other. So we need to run one term out of this series so that it starts at k equals 1. And at that point, they'll both be starting at k equal 1. So running off one term of this series is plugging in k equals 0. So that would give us 2 times 1 times c2 x to the 0, which is just 1, of course. And now we have our series starting at k equals 1. And since both of them at this point start at k equals 1, why don't we just factor that sigma out of both of them right now, as well as the x to the k will factor on the right-hand side. So we have this thing. All right. Let's form our recurrence relation. So we're going to set this entire coefficient here equal to 0, and we're going to solve for the largest indexed ck, so that would be ck plus 2 in this case. So we can see that ck plus 2 is equal to c sub k minus 1, all divided by the product k plus 2, k plus 1. Okay, and this recurrence relation holds for k greater than or equal to 1. Right? It does not hold for k equaling 0. This was a second order differential equation, which means that we expect there to be 2 unknown constants. So we're going to now just write down all our constants, and we're going to use the recurrence relation as needed to write them all in terms of the first 2 constants. So we have c0 equaling c0 and c1 equaling c1. The first 2 constants are arbitrary for the second order differential equation. However, all the other ones can be written in terms of c0, c1, whatever. So what is c2? Well, we cannot use the recurrence relation for c2 because in the recurrence relation, notice that k must equal 1 or greater, which means the earliest coefficient we'll be able to use the recurrence relation to find is c3. That's the k equals 1 case. So how do we find c2? Well, this term has to equal 0 on its own. So we have 2c2 equaling 0. That just tells us flat out that no matter what, c2 is always going to equal 0. So c2 is 0. All right, but from now on, c3 and onward, we will be able to use the recurrence relation to get all of these numbers as needed. So let's use the recurrence relation to find c3. So again, in the c3 case, that is k equaling 1. So c3 is equal to k equal 1. So that would be c0 divided by 1 plus 2 is 3, and 1 plus 1 is 2. So that's what c3 is. What is c4 equal to? c4 is, that's the k equal 2 case. So that would be c sub 2 minus 1. So that's c1 divided by 2 plus 2 is 4. 2 plus 1 is 3. So c1 over 4 times 3. All right, what is c5? Well, that's k equaling 3. So we know it's going to be c sub k minus 1, so that would be c sub 2 over 5 times 4. But we're not done because c2 is actually equal to 0. So c5 is equal to 0. Okay, what is c6? That's the k equals 4 case. So that would be equal to c sub 3 over 6 times 5. Well, what's c sub 3? C sub 3 is c0 over 3 times 2. So this is really going to be c0 over 6 times 5 times 3 times 2. And no, that is not 6 factorial. It's because we're missing the 4, right? That's just unfortunate. Okay, let's do one more, c7. So that's the k equals 5 case. That would be c sub 5 minus 1. So that's c sub 4 divided by 7 times 6. And c sub 4 is c1 over 4 times 3. So this is c1 over 7, 6, 4, 3. Okay, and again, that's not 7 factorial because now it's missing the 5 and the 2. Okay, so, well, what the heck is our y, right? That's what we're really after. So remember, this is what y is. So, well, we found all our c whatevers all the way up to c7 so far. So we could write this, of course, as c0 plus c1x plus c2x squared plus c3x cubed plus dot dot dot. We actually know all the terms up to c7. And if we wanted even more, we could certainly know how to find more. So let's plug in what we know. Of course, we are saying that c0 and c1 are arbitrary constants, but then everything else depends on c0 and c1. c2 is actually 0, so let's just skip that one. c3 is c0 over 3 times 2. c4 is c1 over 4 times 3. c5 is 0, so let's skip that one. c6 is c0 over 6, 5, 3, 2. That would be x to the 6. And then we also found c7, which is c1 over 7, 6, 4, 3. And there's an x to the 7 there, plus dot, dot, dot. Okay. Now, this is not incorrect, but it's a little unsatisfying. It's also not that great that we have c0, c1, c0, c1, c0, c1. We know that the general solution of a second-order homogeneous linear differential equation should be a constant times some function plus a constant times some other function. And those two functions form a fundamental set, right? Well, we are really one maneuver away from having that form. If we write this as y equal c0, and we're just going to factor c0 out of every term that has a c0. So we're going to get 1 plus x cubed over 3 times 2 plus x to the 6 over 6 times 5 times 3 times 2 plus, now we don't have any other c0 terms written down, but that's good enough. And we're adding to that c1 times all these terms with a c1 factored out. So that's x plus x to the 4 over 4 times 3 plus x to the 7 over 7, 6, 4, 3 plus doot, doot, doot. And there we are. That is our series solution to that differential equation. If you want more depth, you certainly can go and use the recurrence relation to find more coefficients and get a higher degree of precision with this particular function. Is there a pattern from which we can extract and write this in a beautiful sigma notation, which we love? Sort of, but we're not going to be doing that. Unfortunately, those patterns are not very easy to articulate. Now, the next question is, do you have to leave the factors all multiplied individually like this, or can you actually just work out the actual numbers and write them there? That's entirely up to you. These numbers get pretty large if you actually multiply them all out. I just didn't want to do that, which is why I left them like this. I believe that your book solutions are mostly written in this particular type of form. All right, so here we have a homogeneous linear second order differential equation with non-constant coefficients. So yeah, let's use power series. Okay, so we'll let y be of this form. And therefore, y prime is n equal 1 to infinity of n cn x to the n minus 1, y double prime, n equal 2 to infinity of this thing. Okay, so we will substitute these pieces into the differential equation. So here's the differential equation. So we have x plus 1 times y double prime, which is this series here, plus y, and that's all equal to 0. All right, so before we balance the powers of x, let's distribute this sigma here into this binomial. So we're going to get x times the series. Well, that's just the series, but with the power of x incremented. So this will be x to the n minus 1. Then we have this series distributed into the 1, so that's just the series, exactly as it is. And then we have this guy. Okay, so now let's balance the power of x's. So we want k here to be n minus 1. We want k here to be n minus 2. And here we want just k to equal n. Okay, so what are we going to get? Well, this guy will start at k equal 1 to infinity, and all the n's are going to be k plus 1. This guy's going to be k equals 0 to infinity, and all the n's are going to be k plus 2. And this guy's going to be pretty identical to what it was, but with a k. All right. So now we have x to the k in every single series, but we are not balanced with respect to where they all start. So we need to run off one term from this series and this series so that they all start out at k equal 1. Okay, so running off the k equals 0 term from this series, we're going to get 2 times 1 times c2 x to the 0. And running off the k equals 0 term on this series, we're going to get c0 x to the 0. Okay, so now they all will start at k equal 1 to infinity. And this is as good a time as any to combine them all to a single series while we're at it. So we're going to factor that sigma out, and we're also going to, on the right-hand side, we'll have our x to the k. So everything in the middle here will just be the other stuff. All right, so it doesn't really matter what order we do things in, but we know this is going to equal 0. So we might as well get our c2 in terms of c0 here. We have 2c2 plus c0 is equal to 0, and therefore c2 is equal to negative c0 over 2. Okay, we'll worry about that in a minute. Let's go over here and get our recurrence relation. And we will do that by isolating the highest indexed k here. So that would be the ck plus 2 after setting this quantity equal to 0. So we can see that ck plus 2 is equal to negative ck, negative k plus 1, k ck plus 1, and that's all divided by k plus 2, k plus 1. All right, so let's work out some constants. The first two are arbitrary constants, so they're just going to be defined to be themselves. And we actually already have C2, which we worked out as negative C0 over 2. So very good. C3 is, well, that's the k equals 1 case in our recurrence relation. So we can see that that's negative C1 minus k plus 1 is 2, so we have 2 times 1, and then ck plus 1, so that would be C2. And this is all over k plus 2 times k plus 1, so that would be 3 times 2. But what is C2? But it's negative C0 over 2. So this is actually like negative C1 plus C0 all over 3 times 2. And we didn't last time, but this time let's just multiply them right out, so we get a 6. Okay, well what about C4? Well, that's just the k equals 2 case. So C4 is negative C2 minus, again, k is equal to 2, so this is 3 times 2 C3, and that's all over 4 times 3. Okay, well what's C2? C2 is negative C0 over 2, so this is going to be positive C0 over 2 minus C3 times 6 is actually just the numerator of C3, so this is going to be negative C1 plus C0, and this is all over 4 times 3, which is 12. We have C0 over 2 minus C0, so that's going to be minus C0 over 2 plus C1, and this is all over 12. Let's write it as negative C0 over 24 plus C1 over 12. This particular one's getting fairly complicated, so why don't we stop here, because we actually have plenty of terms in order to have a pretty good look at what our series is going to look like. So y is of course C0 plus C1x plus C2x squared plus C3x cubed plus c to the fourth x to the fourth, and we actually have all of those coefficients. So let's go plug this stuff in. C0 is C0, C1 is C1, C2 is negative C0 over 2x squared, C3 is, well, let's write this as negative C1 over 6x cubed plus C0 over 6x cubed, and we're writing it this way because we know we're going to split this into two separate series in a little minute. And C4 is minus C0 over 24 x to the 4 plus C1 over 12 x to the 4 plus do. All right, so y is equal to, factoring out c naught, we're going to get 1 minus 1/2 x squared plus 1/6 x cubed minus 1 over 24 x to the 4 plus or minus, who knows what comes after. We could work it out if we needed to. And then plus c1 being factored out of its terms. So we'd have x minus 1/6 x cubed plus 1 over 12 x to the 4, and then plus or maybe minus, who cares? We could work it out if we needed to, but there we are. That is our general solution.